Good afternoon to everyone, and first of all I'd like to thank the organizers of IMANCP for giving me this opportunity. So I mentioned I'm Laura Carlini and I'm from Istituto di Struttura della Materia of the CNR in Rome. And during this talk I will present you some recent works carried out by our groups on linear and cyclo-dipeptides. So, dipeptides are the simplest polypeptides present in nature. They can be formed bonding to amino acids via peptide bond. The formation and disruption of this bond in cyclo and linear dipeptides, you can see the structures here, can be very interesting for different scientific as well as practical purposes, from the study of the origin of life to the development of self-assembled nanostructures. In this talk, I will present you three studies, which are the cyclization of a linear species, photoionization and photofragmentation of aromatic cyclodipeptides, and I will present you some preliminary results on experiments beyond the isolated molecules performed on films and clusters of dipeptides. So the first study is the thermally induced cyclization of this linear species, which is the linear phenylalanine-alanine dipeptide. This work is related to an important message, which is a warning about handling the linear species. It is known that they can be more fragile or more reactive than the cyclospecies, and in this case we found that we have an efficient cyclization in the condensed phase, triggered by the temperature and catalyzed by water. To prove this mechanism, we combined different experimental techniques with theoretical simulations, starting from the time-of-flight mass spectrometry, in which we observed a sudden and huge emission of water when we measured these samples, which lasted for several hours. Then it decreased, and then at the end, at the sublimation temperature, you can see only the parent ion of the cyclospecies and its related fragment, while we never observed the mass over charge ratio corresponding to the linear parent ion. Then we performed thermogravimetric and differential thermal analysis and infrared and Raman spectroscopies in our laboratories in Rome. Now, due to the lack of time, I will discuss only the infrared measurements as they can provide the fingerprints for the cyclization in the condensed phase. Okay. So we performed infrared as well as Raman measurements on the pristine linear pheala, the residual pheala sample after TOF mass spectrometry, and on other cyclospecies, not being commercially available the cyclopheala itself. The comparison between the experimental spectra and the simulated infrared spectra allowed us to establish that all the main spectroscopic features we observed in the infrared spectrum of the residual pheala after TOF mass spectrometry in red are fully compatible with those of a cyclospecies. These fingerprints, in particular in the region of NH, CH, and CO vibrational bands, have been individuated and listed, proving that we have cyclization in the condensed phase. And the same is for the Raman measurements. Then our colleague Giuseppe Mattioli performed also calculations on the reaction mechanism leading to this cyclization. And here we have three different paths. The first two are intramolecular reactions. The first one is related to the formation of a four-membered ring. And then path 2 is related to the formation of a locally stable intermediate. But then in path 3, which is an intermolecular reaction, we can see that the water molecule plays an essential catalytic role. As a single water molecule can basically halve the energy barrier for the process. And also our colleague performed some preliminary calculations, finding that the interaction with the other molecules in the bulk, together with other water molecules produced during cyclization, can further lower the barriers, let's say starting a sort of chain reaction process, so that the cyclization of the pheala in the condensed phase become really efficient. Now, the second work I will discuss is the gas phase characterization of cyclodipeptides containing one or two aromatic amino acids, which make them interesting for different applications. The samples we investigated are reported here, but I will discuss only the case of cyclotryptophan tyrosine to show you how strongly the indole in the side chain of the molecule can influence its fragmentation and the molecular orbital distributions. Okay, on these samples we performed photoelectron spectroscopy and photoelectron photoion coincidence experiment at the SIPO beamline of Elettra synchrotron facility in Trieste using this experimental setup. The main advantage in using the PEPICO technique with respect to conventional mass spectrometry is the possibility to correlate the photoelectron energy distribution with the state selected fragmentation. Also in this case, due to the lack of time, I will discuss only the main results we obtained for the from the PEPICO measurements carried out on the cyclotryptophan tyrosine. But if you are interested, we have two references here in which you can find all the measurements and the simulations we performed for these samples. For example, in this reference, which is dedicated to the photoelectron spectroscopy, we found that these species have show conserved features in the photoelectron spectra due to the presence of this characteristic central ring, which is called, which we can call diketopiperazine ring, which is typical of the cyclostructure, and due to the presence of at least one aromatic terminal. But as I said, I will skip this because we don't have time. So, here on bottom you can see on the left side the mass spectrum acquired during PEPICO measurements on the cyclotryptophan tyrosine, and on the right side the PEPICO branching ratio for the main fragments. The most interesting result we found is that when the indole is present in the side chain of the molecule, its fragment, the 130 plus here in green, will fully dominate the mass spectrum and the PEPICO yield and fully reproduces the PES features, the photoelectron features. To explain this result, we took into account two different theoretical approaches, which are potential energy surfaces analysis and molecular dynamics simulations. So, our colleague Anna-Rita Casavola performed a very detailed analysis finding the most energetically favored fragmentation pathways for all the three molecules investigated. In case of tryptophan tyrosine, shown here, she identified three main channels leading to the production of the indole fragment. The one with the lowest energy corresponds to the direct dissociation from the parent ion. But we have another channel with a very close energy, which is the production of 242 plus, corresponding to the loss of the other aromatic terminal of the molecule, the phenol terminal. Despite the energies are very close, the contribution of 242 plus in the PEPICO branching ratio is smaller than 1%. And this we cannot explain just looking at the energy for the production of this fragment. And so, for this reason, Giuseppe Mattioli and Francesco Porcelli from our institute performed molecular dynamics simulations along selected fragmentation trajectories, following the charge distribution and the CH2-CH bond distance oscillations between the central diketopiperazine ring and the two side chains of the molecule. First of all, they found that the ionization produces a fast structural rearrangement from the folded neutral structure into an open cation with a higher distance between the two side chains and with the positive charge mainly localized on the indole terminal. And then, if we follow the fragmentation leading to the 242 plus, the localization of depletion on the indole terminal together with the CH2-CH bond oscillations drives the fragmentation producing the 242 plus, in which we have still a strict localization of the positive charge on the indole side chain. So this results in a rapid fragmentation, producing again the indole fragment. And this can explain the fully dominance of this fragment over the mass spectrum and the pepicoid. Now, the last part of the talk is dedicated to experiments performed on films of amino acid compounds and clusters of dipeptides. The main aim of these experiments was to go beyond the isolated molecules, to answer questions such as can the cyclic structure improve the resistance to harsh environment, or can the dipeptide decomposition triggers and support polymerizations. So we wanted to have a high molecular density, and we wanted to take into account the possible contribution, the possible influence of neighboring molecules. And this is the reason why we let's say, just to detail in a better way, we first of all we wanted to investigate and compare the radioresistance of cyclospecies, cyclodipeptide, with respect to linear ones. And then we wanted to find experimental evidences of possible polymerization mechanism. So here I reported a reference of our previous work, in which, thanks to the work of our theoretician colleagues from Universidad Autónoma de Madrid, we found that the decomposition products after UV radiation on cycloalanine-alanine may interact and recombine to reconstruct the parent ion itself, or can trigger and support polymerization. So basically we wanted to investigate the production of these species. The species we are looking for are 71, which is half molecule, and a 5-oxazolidinone species, which correspond to the opening of the cycloalanine-alanine with a structural rearrangement. After a few slides, you will see their structures. So for these reasons, we performed ion collision experiments at the Ganil facility in Normandy on films and clusters of dipeptides. And I'd like to thank Sylvain because during the talk this morning he gave you already a nice introduction about ion collision experiments and the Ganil and the Aribe beamline at Ganil. So the first experiment has been performed at the Irsud beamline at Ganil facility on a large set of films listed here. These films have been irradiated with carbon 4 plus ions, and the infrared spectra have been acquired every 5 minutes in transmission mode until a final ion beam fluence of 2 to 10 to 13 ions over centimeter square has been deposited on the sample. The analysis is still in progress from both experimental and theoretical point of view. So for now I will show you some interesting results, just for preliminary results for the alanine family, meaning alanine amino acid and cyclo and linear alanine-alanine dipeptide. So here you can see the infrared spectra. In black we have the spectra acquired before starting the ion beam irradiation, and in red the spectra after the last dose. Thanks to our theoretician colleagues, we identified and assigned some characteristic features related to the skeletal modes of the molecule in the region between 600 and 1200. I have a video, but I think it will not work. Just to show you, but you already probably know, that the skeletal modes are vibration characteristic of the backbone of the molecule, so they will involve all the backbone of the molecule. So we use them as an indication for the integrity of the film. So I performed the analysis of the area of these peaks as a function of the dose. For example, here I'm showing you the trend for area 1030 for cycloalanine-alanine in black and 954 for linear alanine-alanine in red. The evolution of the area as a function of the fluence can be represented by this formula as an exponential trend, in which we can evaluate the radioresistance of the film using this sigma coefficient, which is called destruction cross-section. So higher is sigma and faster the film will be destroyed. And so the slower decrease in the area of peak 1030 for cycloalanine-alanine suggests that the cyclospecies may be more resistant than the linear one. And we are very happy about this, as this was one of the hypotheses we wanted to prove. Then we found also some features increasing in the infrared spectra of cycloalanine-alanine, increasing with the dose. According to the simulation, some of them may be related to typical vibrations of the species 71 and 5-oxazolidinone, which we proposed in this work may interact and recombine for reconstruction or polymerization. So obviously these need to be analyzed more in detail, but still it can be considered as a good starting point for future analysis. And finally, we found an interesting result about alanine amino acid. Here you can see the infrared spectra in in green for alanine amino acid before starting the irradiation, and in red after the last dose. In black, we have the infrared spectrum of linear alanine-alanine before irradiation. You can see that the spectra of alanine after irradiation and linear alanine-alanine before irradiation become extremely similar, especially in the region of CO and CH vibrational bands. So we can hypothesize that alanine may undergo a polymerization during irradiation, leading to a linear structures. And this has been confirmed by some preliminary calculations in the region of the CH stretching. Now, the last part, but very few slides, it's about fragmentation by ion collision of isolated molecule and clusters of dipeptides. So here we go at the Aribe beamline of Ganif facility, which is equipped with an aggregation cluster source. And we performed measurements on isolated molecule and clusters of cycloalanine-alanine and cycloglycine-glycine. Also in this case, the analysis is still in progress, so we need the support of the theory to explain the results I will show you. But I will just show you some slides about our observation on the experimental data for the cycloalanine-alanine sample. So here we have the comparison between the mass spectra of isolated dipeptide by photoionization on top, and then we have the isolated molecule and clusters by ion collision on bottom. Just to see, this is the mass spectrum up to the parent ion indicated by the dotted line. Just see some differences between these, these spectra. So first of all, we have a broadening of higher masses in case of clusters, and this may be due to a kinetic energy released during the fragmentation. And then we have another difference, which is in the trend of the intensities of these masses, which is decreasing in case of isolated molecule, while almost constant for clusters. Then here we have the mass spectrum for clusters of cycloalanine-alanine, and we have singly and doubly charged clusters up to 10-20 molecules. One interesting result is that we found new structures in this region between monomer, dimer, and trimer. And if we look at the zoom in that region, first of all we see a mass overcharge ratio of 211, which may be related to a complex 5-oxazolidinone 71, still the same decomposition products we wanted to find, to see, to measure, to prove our hypothesis about polymerization and reconstruction. And then masses 43, 99, 114, and 127 are indicated as the new structures we found correspond precisely to monomer, dimer, and trimer plus these masses. So as I told you, this is just preliminary, so now the analysis is in progress with the support of the theory to explain the results we observed. So basically I finished. Just to summarize and conclude, With this talk, I wanted to pass a few messages, which are first of all a warning about handling the linear species. We know that they can be more tricky than the cyclospecies, but also we could have some smart decomposition mechanism, which is not easy to be identified. So you measure something which is stable and seems intact, but still it is not the linear species anymore. Then the story of the aromatic cyclodipeptides tell us that when the indole is present in the side chain of the molecule, independently of the ionized orbital, the charge will always migrate to the indole terminal, which is then lost as a charge fragment, fully dominating the mass spectrum and the pepicoid. And finally, if we want to investigate the molecular reactivity in search of possible survival mechanism or polymerization processes in harsh condition, we need high molecular density, and we need to take into account the influence of neighboring molecules. Our approach in this case is to study systems such as films and dipeptides by ion collision experiments. So here we have a long list of names. I hope I didn't forget anyone. Otherwise, I will say sorry. But among them, they gave us a huge support contribution for the result I showed you. Among them, we have Robert Richer from Elettra, and Patrick Rousseau and Alicia Domaraccia from Ganil. Our colleagues from Universidad Autónoma de Madrid for the calculations on the reconstruction mechanism and polymerization, Sergio Diaz-Tendero and Dario Barreiro Lage. The theoreticians from our group, among them we have, I told you, Anna Rita Casavola, Giuseppe Mattioli and Francesco Porcelli, and many others. I won't list all of them. And obviously I'd like to thank all of you for your kind attention.
We have time for 2 or 3 questions.
Thank you for the really nice talk. I'm curious about the mechanism that you've shown with water.
Mm-hmm.
Have you a feeling that to have more than one water molecule will even lower even more the barrier, or it's really one water mechanism that making the game?
Okay, yes. I will try to answer as good. But I'm not a theoretician, so I will try to answer as good as I can. But here, this calculation has been made obviously for an isolated molecule, and it has been include only a single water molecule for proton transfer. And from this, you can see that the change is really huge. So our colleague tried to include other water molecules and the bulk, but it is not easy to do that. It becomes too difficult to include all these contributions. But according to him, and also as he found some smaller barrier, not too much, but smaller barrier, according to him, the contribution of bulk, because this is a process which happens on the, let's say, on the interface from gas phase and the bulk molecule. And these are zwitterion in the solid state. So the zwitterion is stable in the solid state, but as it changes in the gas phase, as you sublimate it in the gas phase, it will start to be very reactive. And then for each, we saw water in the sample, so we know that there is water. So a single water molecule can half the barrier, and this is good. Then for each cyclization you produce another water molecule. So we don't have, let's say, real proof that we have a chain reaction process, that we have a really huge decrease in the barriers, but the hypothesis is that it will favor the cyclization. So as the water is playing a catalytic role, and more water you produce, and more probably you will enhance the efficiency of the cyclization. And then also the bulk molecule could help the zwitterion to, let's say, to close itself.
Thank you.
Seems we have no other questions and the time is running out, so let's thank Laura again.
Thank you.